So we'll now move to the different criterions that you could use to evaluate the goodness of split. We'll be using the impurity measure to determine if the split is good or not. Impurity is high if data is heterogeneous, meaning very different, or low if it's homogeneous. So this one here is heterogeneous. This whole set is heterogeneous because there are many positive and negative classes in this whole set. Whereas in this one, we have just one class. We want this as much as we can when we do the split. We want to maximize this occurrence. So you'll have lower impurity when you have this one here, the lower plot, compared to the one above. This will have high impurity. So let's discuss some different impurities that we could use. So this is a very basic one, 0, 1 plus impurity. So you're basically just counting the other class in that specific set. The ones that have a lower count. For example, in this plot, you have A and B, and this is your split. So you have set A and set B. This one will have an impurity of 0 because it's homogeneous. It contains just the positive labels. Whereas in set B, we only have the negative class, so it's still homogeneous. So we have a loss or impurity of 0. But if our splitting is something like this, it's a horizontal line, in set A, we'll have an impurity of 0 because it's just one class. But in set B, we'll have an impurity of 1 because it's the minor class and the count of the minor class is 1. Understood? But say we have this example. We have different splits. This is the whole space. We're going to have an impurity of 1, of course, because that's the count of minor class. And if you have this split, AB, for set A, your loss is going to be 0 because it's homogeneous. But for set B, you're going to have 1 because that's the count of minor class there. In this example here, if you have this splitting, you'll have a loss of 0 for set A and a loss of 1 for set B. Look at the following. You have the same loss or impurity values for set B, but they have different splitting. That's why this is a very basic impurity. There are other ways of doing it. So what if we use entropy? So this is a very common way of evaluating models. So entropy came from Shannon's information theory, and this is the equation there. It's not exactly that. This one here, this S, is the number of counts in that specific set. The true entropy equation is just this one, the summation of the probability times log of that probability. But since we are computing the loss, we have to also take into consideration the number of classes in that particular set to give more emphasis to that, of course. And normally it's the weighted average, but doesn't really matter in this context because we're just getting the loss. So the higher it is, then means the model is worse. So we can ignore the denominator. That's why it's just S here. So normally it's going to be like the number of classes in A over the total counts for the whole set. Anyway, that's just the difference between entropy and the impurity, the 0, 1 loss impurity, we instead of just counting the number of minor class, we're gonna compute for this the probability times log of probability, wherein the that probability sub I is just the number of that class in that specific set. So okay, let's compute. For example, this one in this splitting, the loss of A will be this. So -4 because we have four classes, four data points in this set times the what? The probability of let's start first with class 0 or the negative class. This one we're counting the this x here. Since there is none, it's gonna be 0/4. Sorry, Zoom is annoying. It keeps on blocking my screen. I can't see the numbers. Move away. I can't see the numbers. Sorry, it's blocking my screen. Okay, there. So 0/4 times log of 0/4. Of course, it's going to be 0, so it's not really important. And then this one here, the other term plus 4/4 because we have four counts of the positive class in this set. So that's 4/4 times log of that. You're going to end up with 0. Of course, it's the same as the 0, 1 impurity loss because it's homogeneous. So it's a very good split. But if we use the split here, the one in the right, what are we going to get? So for A, of course, it's going to be 0 because it's homogeneous. But for B, the loss is going to be this -3 because we have 3 data points times 1/3. Why is it 1/3? Because there's one occurrence of the negative class in this set. So 1/3 times log of 1/3 plus 2/3 because 2 occurrence of positive class over the total count times log of that. So you end up with a loss of 2.75. So if you add them, you'll get a total loss of 0 here and a total loss of 2.75 here. So we know that this one is better compared to this. Of course, this is the same as the 0, 1 purity loss. But how about this example wherein the 0, 1 loss performed bad? Because remember earlier we only got 1, 1, 1, 1 loss for all examples. So let's compute. If we apply that equation there, we'll get the following. The loss for B is 3.245, whereas the loss of B for this different splitting technique will get a loss of 2. So what do you think? Which is better? This one in the middle or this one in the right? Which is a better splitting? Any guesses? Yes, correct. It's the right one because we have lower loss value here. As much as we can, we want to have 0 loss. Okay. So that's it for entropy. But how do we now know how to further do the splitting? Because we don't just stop here. We stop at one split. We have to keep on doing that. How do we now know the increase in performance of the splitting when we add more splits. So we can do that through the information gain. And the equation for that is just the total loss for the whole set minus the sum of the loss for A and B. So for example, the total loss is 3.9. This assumes that you did not do any splitting. It's like the initial state, right? You have that whole space. You did not do any splitting. You simply categorize all the data points as just the dominant class. That's basically this one, this loss value here, very naive. But now we'll introduce some splitting. If we do this left splitting, we're gonna get a loss of 3.609 for set A and 0 for B because it's homogeneous. For the middle one, we'll get a loss of 0 for set A because it's homogeneous, but for set B, it's 3.245. For set for the right graph, we're gonna get a loss of 0 for one for set A and 2 for B. Yeah, it's the same as before. But now we'll add the we'll get the information gain. So from 3.9, we deduct the loss for A and B, and same for others. So we end up with 0.29 for the left, 0.655 in the middle, and 1.9 for the ones in the right. So this means that you gained the most information for this splitting here, this one on the right. Okay, understood. Yeah, okay, I think you understood. Um, the entropy isn't the only way of doing the splitting. I mean, there are different criterion. One popular alternative to entropy is the Gini index. It's a more simplistic equation compared to the ones before. It's almost the same thing, except we don't have the log value here. And we just deduct the whole thing. We just deduct it to 1, right? That's the difference. But the information gain is the same. That's still the equation. We're just changing the loss computation. So for example, we use the same splitting that we have used before. The loss for B here is going to be this because it's homogeneous, same stuff. For the graph in the right, we'll get the following loss. Of course, it's going to be 0 for set A, but for set B, it's going to be 1.333. Why? Because 3 times 1 minus 1 third squared plus 2 thirds squared, you're going to get that. What if we do it again for the other examples? Let's compute. Let's compute. Right. So same with entropy, we got the highest information gain using this splitting here on the right. It still has the best information gain. It's still consistent. Okay, understood. So they're just two common criteria that we use for splitting in decision trees, Gini and entropy. Now, how do we handle continuous values? Because we're dealing with discrete classes before. We simply use the variance. That's what we use for continuous values if we're trying to predict continuous values. So, for example, we have this as label 3, 2, 2, 3, 3, 2, 11, 11, 11, 10, 10. and say, for example, we split it into this. We just compute the variance for this sample and then the variance for this sample. We'll end up with the following values: 15.7 for set A and 0.33 for set B. But what if we have this splitting, which is a better splitting? We cut it here. We'll end up with a variance of 0.3 for both sets. This is a better splitting, of course, because the loss is much smaller compared to this one. This one is 15.7 and 0.33. This one is 0.3 and 0.3. That's how we do it for continuous values. So is there a chance that our tree will overfit? Definitely. Again, if you use all the possible questions, basically, and the possible number of questions that you could have is the whole data set. You ask very specific questions. You'll end up, it will become overfitting. So how do we prevent that? We will have stopping criterion. We could set the minimum batch size. We can set the tree depth. So once it achieves that depth for the tree, we stop. We no longer ask more questions because that will be overfitting. We could also set the number of nodes and the impurity reduction percentage. These are all the things that, well, these are just some of the parameters that you could set when you're using the sklearn model. And they act as regularization method, right? Because we're preventing overfitting. So here's one more example for decision tree on how it does the query selection. So let's start with this one first. The first data point that it encounters is age greater than or equal to 5. That's our threshold because it's the first data point that it saw. So we'll use that. What's the information gain if we add this sorry, we use another threshold value, or we add another threshold, sorry, if we add another question, we'll have this information gain 0.33 for both 25 and 15. So it doesn't really matter. Whichever we choose among the two features will end up with the same information gain. So let's just use 25 ish greater than or equal to 25 because it's the first one that we saw. Right, so we add that. We add that question. Something happened with my Zoom tab. Okay, now that we have added that another question, let's ask more questions to handle this case here because we want to predict this correctly. This one, this X label here. So what's going to be our information gain if we ask the following questions? Is age greater than or equal to 35? Is score greater than or equal to 15? Is score greater than or equal to 25? The highest information gain will come from this specific question. The the score is greater than or equal, is less than or equal to 15. So if we ask that question, we'll gain this much information. So that's the one that we choose for the last question. And now we have handled this problem very well because we can now accurately predict this. So that's how you choose the queries that you have for your decision tree. You check the data set, you just compute the information gain that you'll be getting for all possible questions that you could make, and then choose the best one. And then you zoom in on that particular set left, the one that has a higher loss. You focus on that particular set, and then you ask more questions, more and more questions up until the total information gain is high. right? So this is like the algorithm for decision tree. This is the base case. If they have the same class, then just return it because this is homogeneous. Else you choose the best attribute and threshold, same as the one that we did in this exercise. And then of course you're gonna have the left tree and then the right tree. So yeah, that's it. You just ask more questions, ask more and more questions up until you end up here. You end up using the questions that have the highest information gain. Okay, so there are different tree algorithms that you could use to do that. These are the popular ones. Actually, we're sklearn uses this cart algorithm, tree algorithm, and it's Gini based. If you use entropy based, then it's gonna use DC5. So yeah, these are the algorithms that are running behind the scenes when you use them in sklearn, and it uses the concepts that we have learned earlier, the usage of entropy and Gini based indices. Okay, that's it. Any questions?